is very fresh. So smell it. And it's work that I did with collaborators, David Pedernio, Andrew Cheek, and Patrick Foldenauer. And it's exploring the NSI landscape in a context that maybe people are less familiar with. So using direct detection experiments instead. So I want to start with a hopefully not too shocking fact that the standard model as we know it is incomplete. Now, I've gotten a little bit of flack for this statement because one might get a little bit pedantic with exactly what you mean by standard model. So I have now added the qualifier, the standard model insofar as it's a complete theory of fundamental physics, right? So we know that the standard model doesn't entirely encapsulate the phenomena that we see in our universe. Gravity, for example, isn't embedded in the standard model. But just as interestingly, I think, but I'm biased, the behavior of neutrinos isn't exactly encapsulated in the standard model. So we already know that neutrinos kind of scream new physics at us because they have this property where they have a kind of identity crisis, right? They kind of oscillate between one flavor or another, and that only happens because, well, in order for that to happen, we need neutrinos to have some kind of mass, right? In the standard model, that's forbidden. So already, these guys are saying that there's something out there beyond what we know. And therefore, they're, in my opinion, prime candidates with which to actually search for any further new physics. Direct detection experiments might not be the first thing that come to your mind as a sort of probe of neutrino physics. But as we'll see, they're very, very well placed to do this. So for those of us that don't know too much about direct detection experiments, here's a very nice visualization of what's called a time projection chamber. The details aren't too important. What really matters for us is that we have some kind of incoming particle over here. It will collide with some nucleus, some electron, and it will cause some initial kind of light to scintillate from it. Particle will leave, and as the particle leaves, this light goes into your photomultipliers. You have electrons that are ionized as well. They go into this gaseous phase, and you have some secondary light that's scintillated over there. And the nature of these signals can tell you a lot about the kind of event that actually happened within the target material. And as I say, they're usually employed in the search for dark matter. However, neutrinos are coming. So this is a picture of the neutrino floor. So the neutrino floor in the context of what's called this WIMP parameter space. So direct detection experiments usually look for a very particular kind of dark matter candidate, known as the weakly interacting massive particle. So these guys, this dark matter candidate is characterized by some mass, and it's also characterized by some cross-section of roughly the weak scale. And these are both projections with the dashed lines and actual exclusions derived from current direct detection experiments in this parameter space. And we see that here in this floor, it's essentially somewhere that direct detection experiments will struggle to differentiate between a neutrino event and a dark matter WIMP event. And this is essentially saying, okay, for these experiments here, especially, these projected lines are going to start cutting into this floor. And what that resembles is that they're going to have enough sensitivity to actually see neutrino events happening here. And this floor here, this bump, or the entirety of this sort of raised region is any kind of neutrino that comes from the sun. So these are pseudo neutrinos that we're talking about. And we see that a lot of this parameter space here, they're kind of already saying that they're going to rule it out for WIMPs, right? But the claim here is, you know, dark matter might not exist. So don't worry about dark matter. Let's worry about something that does actually exist, right? Neutrinos, and let's look at those instead. And as I say, these experiments here, so LZ, Dorian, and XENONn, they're the ones that look like they're going to start cutting into the shoulder. So they're very, very good candidates with which to actually do some neutrino physics. So while this sort of event is usually classified as a background, what we really want to do is we want to see, okay, how do we turn this background into an invaluable signal? of potential new physics in the neutrino sector. And that's broadly the setup of this talk. And the way that we're going to go through all of this is we'll first introduce a general parameterization of neutrino non-standard interactions. One that we've developed to cater for both interactions with protons, neutrons, and electrons. We'll then go into seeing how these bounds evolve within this broader parameter space. And then we'll actually look at how direct detection experiments will be suited for neutrino NSI. So first off, I want to chat a little bit about the parameterization that we've developed. Neutrino NSI are typically characterized as like an effective framework, right? So you have some kind of full Fermi interaction, in which you have some neutrino of flavor alpha interacting with some fermion. It can turn potentially into neutrino flavor beta, which is different from the initial flavor, and the fermion goes out again. This is a very general way to model new physics in the neutrino sector because we ignore any potential UV conditions, right? We don't care about the guy that might be mediating the force. We just care about the sort of overall structure and strength of this force. And yes, it's completely characterized by this parameter epsilon, this second Wilson coefficient in the EFT lingo, and it just tells us how strong this force is. So the Lagrangian for non-standard interactions, you can think of as being able to be factorized into a separate neutrino part and a fermion part. So here you have some epsilon, which characterizes the inherent strength of the neutrino part of the interaction, and this psi guy that is essentially telling you how strongly are you going to interact with that particular fermion. And there's no big reason to believe that these two structures should talk to one another. So the neutrino part and the fermion part, so you may as well just factorize that. And we can define this overall, so there's this overall strength of the NSI, which we can then interpret as this product between this flavor only part, so the neutrino part, and the fermion part. And you can think of this as a sort of effective equation in which we have the strength of the NSI with some fermion is equal to the intrinsic strength in the neutrino part of the interaction projected onto a particular fermion. And that kind of projection leads us to thinking about a parameterization like this. So this parameterization was pioneered by Ivan Esteban, Ricardo Matone, and friends. Ivan is coming as well, right? I'm going to learn about this at some point. You can think of this as, okay, if you have an NSI with a proton only, you have the inherent strength of the NSI characterized by this epsilon here. And we project it onto the proton direction. This is just a polar coordinate system, polar parameterization, in which we have strength of your NSI projected onto either the proton or the neutron. Right? So it's just a convenient way to think about NSI. You might wonder, where has the electron gone in this parameterization? There's no reason to believe that NSI wouldn't talk to the electron as well as to the protons and the neutrons. Well, the reason is that in this work, they're only really concerned with oscillation. And oscillation effects enter in the matter Hamiltonian that governs the interaction that neutrinos go in the sun. The electron and the proton both enter together as a sort of sum charge contribution in that Hamiltonian. And what that means is, okay, you can keep the electron and have the sum equal to some number, or you can discard the electron altogether and have the proton and SI be some different value, but that retains the same value that the sum gave. And phenomenologically, they will give you the same result, right? Because this prefactor or this factor here is going to be the same. Right? You can turn epsilon E off, and as long as epsilon P is the same as what it was with epsilon P plus epsilon E, this Hamiltonian will give you the same value. So they kind of throw away the electron and then just have the proton. Now, there's an issue with that, in that if you now throw in, say, NSI with Savant's experiments, which are only probing proton neutron NSI. If you assume that all of the NSIs in the proton direction, that's going to give you a maximal bound, say, if you're looking at over here experiment, right? If you have instead assumed that your NSI were in the electron direction and not the proton direction, your neutron would have to make up a lot more of the interaction to give you the same effect. So this already gives you a bit of an unfair advantage for Savant's experiments. On the other hand, assuming that the NSI is all in the proton direction, means that you're giving oscillation experiments a sort of unfair disadvantage, because if you also have electron NSI, you're impacting the neutrino-electron cross-section, which is proton. Right? There's a sort of degeneracy between NSI effects with propagation and NSI effects with the actual interaction point. So what we really want is a more general parameterization that allows for NSI with everyone, protons, neutrons, and electrons. And that's what we advise in this video. And this is especially crucial for their detecting experiments because they're in this very unique position that they can throw both nuclear recoils and electron simultaneously. So you need a way to try to encapsulate all of these effects at once. Now, perhaps it's not groundbreaking, but if you have a circle and you want to generalize it to another dimension, you may be a student. So our parameterization includes this separate angle over here, this phi angle, which allows you to project into the electron direction, which was assumed before to have phi ranges. So initially, we just had an SI with a proton neutral plane. Now we have this proton electron sphere, in which you can now freely rotate in this hard disk here. So then you're kind of allowing the charge on the side to both lie partially in the proton direction and partially in the other direction. And then, well, this is just, a spherical decomposition of this. So it's nothing, nothing too crazy. The usual assumption, as I say, is either that phi is 0, in which case you have NSI only with the proton and the neutron. Or if you're just looking at electron NSI, phi is plus or minus pi 2. And eta can be 0 as well. But the good thing about our parameterization is that it allows you to have everything. So you get a small thing in the middle. And the holistic approach means that we can capture all sorts of, basically the whole breadth of phenomenology that we expect in NSI. So firstly, there's this propagation effect that I mentioned. So as neutrinos are leaving the sun, kind of talk to everyone. Right? And if they're talking, and if their NSI is switched on, the way they talk to everyone is different to when they talk in the sun. This impacts this thing called the MSW effect, which tells you about effectively how electron neutrinos transition to flavors in the sun, and NSI change that a little bit and change the resonance that they undergo when they're full flame fractions. So that happens at the sun, and then as they propagate, they oscillate as they usually do in vacuum, and then they hit the detector. And at the detector, you can have another NSI contribution from the fact that you have a non-standard cross-section that you have to deal with. And with this parameterization, so before, the parameterization allowed you to maybe look at this and not this, or remove this and just look at this. Now what we can do with our parameterization is look at both. And to look at the rate that we expect, so this is a xenon detector. I think, anyone recognize it? Maybe it's on xenon, who knows? But it's a xenon detector. So in they come, and what we want to do is we want to have some measure of the rate of recoils that we expect at a given energy.
So in the process of nothing happens in the production.
No, not the production. But it's a good point because so in our Lagrangian, we're only dealing with nuclear interaction, whereas every single neutrino producing interaction with the sun goes through charge current.
Yeah.
So that's a very good point because we panicked at one point. I know we have to take this into account, but no. So yeah, so you want to measure, we want to know what the rate is like. And there's one very usual way that people calculate the rate, and it tells a nice story. So typically, we calculate the rate of neutrino scattering at an experiment like this by this equation. So we sum over all the flavors and we integrate with the sum energy, that's fine. And the story this tells is, okay, we go from electron neutrino production in the sun, so there's some measures how you can get this. If that electron neutrino oscillates into some flavor alpha with some probability, and then you convolve that with a cross section for that flavor alpha. Right? That's typically the story. It's usually how people do it. And we go, yeah, as I say, it's nice and it's like a nice story arc. Production, oscillate, interact. This, however, is wrong in the general NSI case. This was very, very recently pointed out by Coloma and Kelly Martone in Madrid. And they argue that, okay, if you have an NSI that can lead to flavor changing neutral currents, which is to say that it's not diagonal to the flavor basis, you have to stop worrying about potential coherence effects that you expect as the beams, because as beams coming in, it's composed of a coherent superposition of flavor eigenstates. So you need to be able to capture the potential correlations between different flavors that's going to happen. You can't just go from, you can't see that you have a muon neutrino and project it in the muon with a muon cross section. You have some superposition of different flavor eigenstates. And you have to have some way of capturing the correlation that you can get between different flavor eigenstates. And this is a bit of a weird point. Bear with me. The takeaway is that you can't do this projection with a coherent beam onto any particular flavor and convolve that guy with the cross section for that flavor. Because if you do that, you can miss very interesting physical effects, like blind spots in the experiment, which I'll go into as we go. So the correct approach is instead to see neutrinos going through this sort of story, in which they're firstly produced, they oscillate into a coherent superposition of flavor states by some S matrix that governs the propagation of these neutrinos. And then that coherent state interacts by some other S matrix and then flies off into some arbitrary final state. And to get the total amplitude, we have to sum over all flavors beta. But we know that the differential rate is going to be proportional to some square matrix element, like some square amplitude. And there's some, we can chat about this after if people are interested, but there's some algorithm that goes into here. And ultimately, what you'll arrive at, if you follow this quantum mechanical approach, is that you don't have probability times cross section, you instead have an expectation or a trace of this sort of generalized cross section that can capture these correlation effects between different states. So here you have a zeta, which is a generalized scattering cross section, and a rho, which is a density matrix that captures the full evolution from electron neutrinos to however they are on Earth in different planes. And this is very important because this sort of difference in treatment can really impact the limits that you might draw within this line. So the question is, using this closed formalism, using this new parameterisation, how is it that NSI limits from the past, right, when assumptions are possibly made on Y, evolve within this new framework? So we're going to try to generalize this into our parameterization, and there's lots of different neutrino experiments that we could look at to do this with. The list is, it's countably many, but it's many. It's a lot. So we just focus on two experiments. So firstly, this XENONNT liquid oven experiment, which is essentially like the coherent experiment they ran in 2017, where they first found they discovered coherent plastic neutrino-nucleus scattering. But instead of doing it with cesium iodide, we're doing it with liquid oven. And then we're also going to look at an oscillation experiment. So in particular, phase 2 data for the CENONNT. And it's as I say, it's a good tasting menu because with XENONNT, we probe just the 7th cross section, whereas with an experiment like Dorian, we probe both the eaves, as in the elastic neutrino-electron scattering cross section, and you probe propagation effects that can happen in the sun. So firstly, XENONNT. So the way we do this analysis is we take, so here's the measurement of the spectrum. We essentially just take the data that they observe and we compare it to the spectrum that we would expect with NSIs would show. That's it. And what we want to do, the point of this is that we want to embed it with our parameterization. So we're going to vary our new angle phi and see how these limits are going to vary. And importantly here, we don't care about this traceability, right? Because there's no oscillation that really happens within small v length. We're just looking at mu neutrinos, anti-mu neutrinos, electron neutrinos remaining as they are, and then interacting with an alpha nucleus. So we do this, we embed it in our parameterization, and we find something that looks like this. So really we have 6 figures. I'm not going to give you 6 figures, that's too many. I'll give you 2 figures at a time. And typically there'll be EE and E tau. And typically what people do is they'll go to phi equals 0 and they'll draw a limit here, right? So then their interval, the allowed interval would be wherever this phi equals 0 line crosses these green bands. And then you say that this is your allowed interval. This is done actually for just an up quark NSI. So in the lingo of parameterization, that just means that we fix eta to be some value. So eta is the angle between the proton and the neutron. Some eta is basically saying that you just have up quark NSIs. And fixing that, we then vary phi and see how these bounds vary. And quite predictably, we see that they generally weaken. Right? So as we go to phi plus or minus pi over 2, you're saying that NSI is going to be more with the electron than the proton. And that means that the neutron has to pull more weight to give you the same effect, which means that the value of your NSI typically is more strong because you have fewer particles talking in NSI. The second minimum here is due to a cancellation that happens between the stellar model cross section and the NSI cross section. This happens anyway. But you see that this minimum also evolves with phi. And here for epsilon e tau, same kind of thing. You have a general weakening of the limit as you go to very phi. So for Borg-Xeno instead, so our top of the line neutrino flux measurer, they look at the sun and they can tell you very well what the fluxes of different solar neutrino components are. So they've measured everyone now, I think they've measured PP, rhythm 7, PEP, HEP, boron 8, and they've most recently measured the XENONnt fluxes, which is incredible because they're in this sort of weird background region where they're kind of highly over here and the background's really high, so it's difficult to kind of the background. But I believe the high statistics they've seen XENONnt. And what we can do is we can take the phase 2 fit of the PP, rhythm 7, and PEP rates to play the same game. So we're doing exactly the same thing. We're looking at how their bounds, which might usually be quoted at phi 0 or phi plus minus pi over 2, corresponding to either only proton interactions or only electron interactions, how they're going to vary as we change phi. So we do that and we find this. So these are more interesting looking plots, I think. So phi equals 0, it might look like we have a bit of an asymptote, but we don't. So a phi is 0, we can still constrain NSI. And these effects are purely due to propagation. Because phi is 0, you're just talking to the proton. So there's no electron contribution, there's no contribution to the electron cross section. But plus or minus pi over 2, you have maximal change to the neutrino-electron cross section. So then you can derive stronger bounds. Then in between, you have a general weakening of bounds, which you expect as well. These little guys.
Sure, yeah.
Yeah, so these are probably not really there. So this is a sort of artifact of the fact that we're trying to just use the total rate as in our statistics, right? So there are points in the parameter space where the spectrum that you expect for the rate is shifted, or when you integrate into it, the number of events remains the same. So these are like little fine-tuned regions where you happen to repeat the standard model expectation. Right? But this is something I've also confirmed. If you were to use spectral information, these values disappears could do good statistics. So they're still there, because the rate isn't hugely different in these values anyway. But if you're doing like a 19.5 second with double the net, then they do go away. But yes, so the point of this whole game is that we're trying to connect plus or minus pi over 2 to 0 to see how these values are shown. So this is a good way to kind of visualize how different NSI will actually be mapped onto varying degrees of phi. And the same thing goes for, say, epsilon e tau, where here you have some cancellation effects high up that are due to both propagation effects and cross-section effects. And then here is a good place to ask, how does the trace formulas come into play? Because here, you do have to stop worrying about the fact that your beam is in coherence position of different kinds. So this is using the trace formalism, but we can also do it not using the trace formalism. You see that actually you can get quite a big effect. So if you don't consider this trace, for any on diagonals are fine. On diagonals, it happens that it's a trace. So for on diagonals, you're always going to get the same kind of effect with or without a trace. But for off diagonals, the game is different. For any off diagonal element, you're always going to have a term that's proportional to an off diagonal density matrix element, which is linear and acts as essentially as an interference term in the standard model and NSI. If you don't take that into account, the picture of the intervals that you expect is quite different. It's not alien to the actual, to when we uses the trace formalism, but it's very different to the true picture. For example, here we have this little valley. This is from Newtown, in which you have an interference, like a linear interference. See this valley here? See this one? Where the standard model plus interference term act in such a way to constructively interfere with one another and make the effect larger, and therefore this region here is more constrained. If you don't include that, that effect disappears. So the point of this is just to illustrate that it's quite important to include something like this. If you want to draw accurate bounds, it doesn't have to be with phi, but in any space, right? You can do the Cartesian equivalent of this, epsilon p, epsilon e, epsilon n. The trace formalism is still something that's important to take.
I think you did explain the step problem. What value, how we calculate, or what value of eta you take, and how we calculate them?
For this, so for the sevens case, we took eta is arctan of a half, which just means that it's an up half NSI. For here, we're taking eta of 0. So here we're assuming that you just have contributions in the chart effects. There's no contribution for you. So eta 0 is like you have your epsilon p, epsilon n. Sorry, we have epsilon n, epsilon p. Eta 0 means you're entirely in the proton electron. And if phi is non-zero, then it means that it's somewhere in the proton electron. Right? So here we're saying, okay, at phi 0, you have a general weakening of the limits. Because now all your effects have to come from the proton, right? And you're looking at electron scattering, so that's not going to be impacted if you have proton interactions. But propagation effects do come into play, which is why you can still draw there. But it's true, generally we want to be agnostic about eta as well, but just to show how these limits vary in the space.
If you don't change the beta values, do they drastically change, or more or less?
As in the shape?
Yes.
I imagine they will change quite a lot. Because this is like a slice of the bound. Really, this is like there'd be some eta axis, and then you'd see if these like exactly. But that means that we need a global state in which we allow everything. a point that I'm coming to very, very briefly. But the takeaway here is that previous NSI constraints that only assume that phi goes in one direction, which is equivalent in another framework to saying that you have NSI only saying with the protons and neutrons, or NSI with the electrons. They're not entirely representative because generally they'll either weaken or strengthen depending on what assumption you make with this thing called phi. Our parameterisation enables you to fill in those gaps quite easily. They're a very intuitive way to visualize how things are going to evolve. We find that these constraints evolve quite non-trivially over phi. They have all these different weird features like these values and stuff. It's not a trivial exercise to see how these limits fit in that parameterization. And very importantly as well, it's very important to use this pre-formalism to draw accurate values. If you don't include it, you end up missing really interesting. So with all of that in play, ready to explore the reflection experiments. So now that we have this parameterization that gives you phi, i.e. it gives you effects of the nucleus and with the electron, we can more holistically play with the reflection experiment because they look at both neutrino-nucleus and electron. And we want to consider these experiments, so upcoming XENONNT, I say upcoming, it's an upcoming full projected XENONNT and LZ, and the far future Dorian experiment. And the reason we want to include these is because, as we saw, these are the experiments that are going to start cutting into that neutrino shoulder. So for all of these experiments, we're going to be considering the solar neutrino rate we expect, which is something that these guys are definitely in the near future. And to, I'm a phenomenologist, right, / theorist. I'm not an experimentalist. So we do, I think, in my humble opinion, a good job of folding in experimental patterns, like efficiency functions, these are resolution, smearing, backgrounds, all of this stuff. And which is something that we can also correlate with xenon people and say, look, we get these many neutrino events, how many neutrino events do you get? Okay, that's something that's happened. But the main point here is that we're trying to be as true to the experiment as possible. So we're not just considering some, some hypothetical sort of experiment, but we're really trying to model these experiments, see what they can do. And we also derive from the recent LZ result, and also the electron recoil results of XENONNT almost last year. So this is not the electron recoil result that said, oh, look, we have excess. This is the one that said, it's very sad, we don't have excess. Okay, so for creating the limits with the data, we use the data and we use the statistics relevant for that data. For deriving our projections, we follow this algorithm. So we assume that we see exactly the same one. We then fix some angle because we're coming back to the point. It's very difficult to do everything at once. It's not impossible, but it is very doable. But just for the purposes of this study, which is to motivate upcoming detection experiments from the NSI space a little bit more in a more focused way, we're just going to say let's just fix phi. We then choose an epsilon and a value for the remaining angle, and then we calculate the expected number of neutrino events within a prescribed number of bins. For nuclear recoils, we just do one bin because most of the signal is contained in one bin. For electron recoils, we consider bins of like 5 with similar to the resolution that we have at that point. And then we find statistically 90% confidence limit that you can go with this slides. One very important point is that we do this only one parameter at a time. I appreciate that this is not playing the game entirely fairly, because, as has been pointed out, people in industry, it's important to consider everything in a global way. because you can have degeneracy, you can have cancellation. So to draw something accurate and representative of what we really expect, we really want to do a global analysis. And I flash this now. So I think incorporating trace formalism as well as the detector effects that we modeled to perform such a global study within this general parameterization is a really important next step in this work. That's enough. So, okay. So just to flash some of the rates that we expect to see. So this is a nuclear recoil rate for an epsilon EE turned to 1 and all the other is 0. This is like saying you have an NSI just with the proton. So black is the standard model, red is with this NSI, dashed is ignore detector effects, red is included. So the red here, or as in the solid, is included. So with the solid, we have efficiency effects, we have resolution effects. We don't have any backgrounds for nuclear recoils because that's a realistic aid for upcoming detection experiments, or at least for the background to be very, very low to the neutrino signal. And for electron recoils, that's a bit of a different story. For electron recoils, we have something that looks a little bit more like this. This is for an epsilon EE, now 0.1, and eta is still 0, and phi is pi over 2, which means that we're now entirely in the electron direction. So again, black is standard model, red is NSI. Here we've got a few different funky things happening. So firstly, we have an expected background for these guys. So this is, I forget what this might be, lead down here. But then as we creep up, this is the double BTK of xenon 136. And these little steps correspond to the sort of trionization effects that we expect in an atom. Like if a neutrino comes in and bumps into an electron, we don't expect all the electrons to be released. Right? You only expect those electrons to be released that can be freed. Right? If you have a really low energy neutrino, it's probably not going to free any. For high energy neutrinos, are going to start freeing more electrons. And then here you can really see, I think, the efficiency happening here and this mirroring. So this is just to kind of showcase the vector effect. So okay, so when you plot the first,
Actually, sorry, that's electron.
this is electron.
And the previous is very nucleus.
Yes.
I would have thought that like below 1, the nucleus efficiency goes to 0. The electron efficiency climbs up. It's like the response to the nuclear threshold of nuclear is worse at low energy. Am I missing something?
No, I think that's exactly it. I think here, so I think there's quite a sharp drop off here, but for the efficiency,
Oh, yeah, the drop off is like beyond what you're showing.
a little bit, yeah. There's still, you can see the drop off there.
It's a log scale,
There's also a log scale.
and that's 2 things. So it's already you're already down like percent. Actually, you go. But that goes to 0 and quickly, right? I would think that actually would fit.
Was in the
Because
drop off
electron-
is
the electron-
yes, but so in the electron channel here we're talking because this is electron equivalent energy as well.
Oh, so okay, so it's
So it's a different, it's difficult
Yeah,
to
okay.
punching back.
Yeah.
Okay. So that's a good point because it looks kind of counterintuitive.
Yeah.
So this is money plot first. So this is again EE and E tau, and we're now drawing limits in this parameter space. So it's a bit busy. The lowest ones, so this purple, will be dull, and then always will be followed. That will be followed by XENONnT and then LZ. And these red bars here are from the global allowed intervals derived by Coloma, Michele, and Madrid people. And here, and this is a global analysis of this is something to keep in mind. So this here is when everything on at a time, and they also consider lots of neutrino experiments, not direct detection experiments. And here the point is that we see that these limits are coming into these are narrow limits. So even for experiments like XENONNT and LZ, which are nowhere near the power of Dorian, I'm going to start coming into these regions here as well. There's some interesting features going on here. Firstly, you have this sort of asymptote there. So this and that asymptote here. So this asymptote is due to a cancellation between proton NSI and neutron NSI. So if you have a negative eta, it's like you have a positive proton contribution and a negative neutron contribution. So you can have somewhere where these contributions exactly cancel for any value there. And this happens exactly there. You have this band here, which is due to a cancellation that happens between the BSN and the interference node. And importantly, because this is a diagonal NSI, you also have it for the off-diagonal NSI. And the off-diagonal cancellation only happens because you use the trace forms. If you remove it, there is no cancellation. So that's another kind of push for using this treatment. Money plot the second is the electron recoil plus nuclear. So this is using the same experiments, but now let's look at electron recoils and nuclear recoils separate. So here plus or minus pi over 2. So I'll get them into the colors first. So we always have red as Darwin here, and then we have XENONNT, and then we have LZ. Plus or minus pi over 2, we have them cutting into these green bars, and these green bars are the recent results from Madrid people again, using xenon-based tube. So this is a dedicated study with NSI with xenon-based. And here we see that their detection experiments look like they're doing a pretty damn good job in this landscape as well. The solid orange and solid blue, which made the solid blue before, are actual values. These are actual limits that we've derived using the data from last year. And we see that they're not really competitive as such at the moment, but okay, it's a log scale, but even XENONNT with their electron recoil data, it's kind of encroaching on more XENONNT, which is really exciting because they're not a neutrino experiment yet. And I think this plot is really cool because it really elegantly shows, I think, this complementarity between using these two different channels. If phi is pi over 2, okay, your nuclear recoil limit is going to be bad. You're going to have pretty good electron recoil. And as you weaken phi and you go to phi 0, your electron recoil is the sensitivity to those is going to fall off. But that doesn't mean that your NSI sensitivity will fall off, because you gain sensitivity to nuclear. So you have this complex, as you lose sensitivity in one channel, you simultaneously gain it in the other. That is incredibly unique to direct detection because they have this ability to probe both of these channels at once. So the takeaway for direct detection experiments is that xenon-based direct detection experiments, as they're progressing, are going to become on a collision course of the neutrino floor/fold. As I just said, they're going to give us really cool complementary information within nuclear recoils and electron recoils. And from the looks of our analysis, they're going to start carving out new NSI. My point here is, anyone here is a huge direct detection experiment documented enthusiast. Don't worry, the neutrinos are coming. So to summarize, neutrinos are taunting us with new physics, so we better look at them. Current NSI treatment, the current NSI parameterisation doesn't holistically treat the whole space because it kills the electron. Our new parameterisation is set towards greater generality. Bounds from neutrino experiments can evolve pretty rapidly in this new parameterisation. And detection experiments are going to be invaluable in this landscape. So my main point here is that they're going to become key players in the search for non-thermal neutrino physics, and this, along with their search for dark matter, will give them a compelling research mission beyond it.
Okay, so, questions for, yeah.
So you kept referring to the Coloma and all as the Madrid people, but I know that you have a lot of collaborators who are also Madrid people. So when is the global fit in this new generalized framework?
One of the two worlds going to collide.
Yeah,
So they have in fact been working on exactly the same kind of idea. So they've also done practically this parameterisation. They didn't call it phi for some reason. Phi is the obvious angle. So there you go. But they're looking into doing exactly this plot with by varying this. And in fact, the reason I know that this goes away if you include spectral information is because they have done that. Okay. So they're looking into exactly this. And we've spoken, we want to try to marry the two parameterizations together and then you should do something cool like a global fit with neutrino experiments.
For coherent data, so you use the liquid data. There's lots of rearrange.
Yes.
So, but why can you use cesium iodide down? It's much more.
So you have to think about it. The point more of all of this wasn't to draw an actual limit. It was to just showcase the importance of considering the electron as well. So you really see how these limits could evolve if you now start tuning up the electron. So same thing as for xenon. It was just a point. The point to be made was just okay. Let's assume that we have some angle phi in between the two, and let's see what happens to it.
Is it because there's a different ratio between cesium iodide and so you were trying to exploit some relative abundance or addition?
But we could have, as I said, we could have just as well used cesium iodide.
Oh,
Doesn't matter. We use this because it was easy to do. Because in a previous work, we were looking at hidden photon sensitivities.
already the same data.
Yeah.
Okay, so you.
But as I say, like definitely we could derive some limit in this space using their data, using CMI data. But the key point was more to explore this evolution of limits than it was to really set. And an award-winning limit.
So also for this electron record or electron scatter. So why don't you use the reactor within the
Oh, as in xenon.
or
Yeah. I think it probably will also.
Yeah, because also you have gamma
Mm,
already. You have this.
Yeah. So definitely. That's also something that we could use there. But here we also with xenon wanted to make this point of the solar neutrino.
Yeah, but the reactor neutrino also is solar neutrino. So it's a PP change.
I see.
So that's more or less introduced by your reactor.
But we definitely could do that as well.
And also the xenon, I'm wondering like between xenon and ton and the reactor. Okay, you showed xenon and ton.
As in here,
Yeah.
as in how these lines would look if the bars have been reacted. Yeah, so as in if let's say that these bars were instead of reacted. Yeah, right. Yeah, that's a good point. So it'd be interesting to see because they'll be tighter, right?
Yeah.
Interesting to see where they would lie here. But even xenon is used in this sort of big pot of the neutrino experiments. These guys used to draw limits, right?
Yeah,
So-
so I'm wondering whether reactor is.
It could very well be.
That's
The point here is just to show, okay, if you're going to consider xenon, then you should also be considering these sorts of experiments. So
That's
LZ,
true.
xenon,
Actually, that what we found that xenon, like competes with coaxium. So, but then reactor can beat both.
Right.
So, like. Pure and transfer would be.
Yeah. Reactor will be electron stack.
Yeah.
Yeah, so here, again, because of this complementarity. Right, so I guess this is where direct detection experiments shine. But they have this unique access to both of these channels at once. So even here, I think you'd get some really crucial information on the, within the NSI landscape if you consider this. But I think certainly it's very true that reactor experiments could already beat these experiments in here, but because they include experiments like xeno-global fits, when you is just look, even experiments like LZ and XENONn, when you take into account a phenomenologist way of modeling the detector effects, they already seem to be pretty competitive.
You mentioned that the flavor part of the NSI parameters don't depend on the formula, but if, like, I'm just like thinking, if the neutrino, if the electron neutrino had an effect with the electron fermion over there, would we have like more NSI parameters?
As in, what if?
Yeah, what if?
Yeah, so if we're talking that, then we're starting to think about charge current.
Yeah.
So electron neutrino are going to interact in different ways with electrons and the new neutrinos. So there it's would likely not be the case that you can form this factorization. It's the whole point is that you can do. It's like, if we were to expand, there it is, expand the sky like this,
Yeah.
and you see this mediator, and you'd have two vertices, one with the neutrino, one with the fermion. In a neutral current situation, you can basically, one can ignore the other, but in a charged current situation, you can't. They're kind of entangled in the way. So I would suspect that you can't perform this kind of factorization.
Any further questions? So then, if not, the best thing,